All right, so chapter 7, we're going to do simple regressions today. We'll do multiple regressions on another day. At the end of the class, what you need to be able to do is, if I give you a data set and give you a scenario, you should be able to take that data and conduct the appropriate analysis, pick the right test, run that test in one of these softwares that we've been going through like SPSS or R. Sometimes you can do it in Excel, and then also report those results in APA style. So that part is not going to be too difficult with the simple linear regression. For SPSS, all you do is click Analyze Regression Linear. You're going to move the DV to the DV and the IV to the IV and OK, and boom, there's the output. I am going to go through some of the underlying mechanics and underlying math for it, but you won't need that too much in the future. It's just more of an FYI, and as you see it, how the math works, it may help you to understand what we're doing. But all that being said, again, we're just going to run it through a stats program and look at the output. This is how we would have reported one of the examples from last chapter, the correlation. The number of cards sent, the number of cards received was non-significant or not significant. Don't write insignificant. And then we're going to list that R. It's the Pearson's R. It's in italics. Our degrees of freedom, n-2, equals, our R was 0.8, and our P was greater than, you see the sign going that way, greater than 0.05. And it was because our sample size wasn't big enough. We can see that from the degrees of freedom. We know it's n-2, so we know we only had a sample size of 5. These are those correlations that we ran last chapter with the friends and their cards sent and their cards received. With correlations, why would you run a correlation? It is to see if there's a relationship between two variables. That's all we're saying, is that there's a relationship between those two. With regressions, it's similar, but one difference here is we're going to say that one variable is going to predict the other variable. And so the variable being predicted is going to be the dependent variable and the y variable, and the variable doing the predicting is going to be, they call it the independent variable, but predictor variable is better said. It's the x variable. Do not confuse this with an independent variable as far as running a true experiment, because a regression is not a true experiment. It is also observational, just like the correlation. With correlation, either one of the variables could have been x, the other one could have been y. They're both DVs in the correlation. But with regressions, one will be the predictor variable, and then the other one is dependent upon that predictor. Let's say we are looking at cards received. And so we got Andrea 10, Mike 12, so on and so forth. Let's say we add a sixth person. We had a sixth person. What would your prediction be for how many cards they would receive? So if we add one more person, if you were to guess, what would your prediction be for how many cards this person would receive? Think about it. Maybe hopefully you got a decent guess. One way that we can look at this is using the mean. So if we go through these and get the mean will be 12. And so if we had to make a guess for a new person that was being added, we would say 12, because that's the mean. That's the only real, the middle value. So that would be, it's not going to be maybe a great predictor, but it's the best we can do if we don't have anything. These are errors using the mean. So here's the line for the mean, which is 12, and then we have each person. So John, he was off by 6. Andre was off by 2. Doris was off by 2. Steve was off by 6. Just like all these other things we've done, if you were to add all that up, that is going to equal 0. What we could do, what we are going to do, is go where we create what's called a least squares equation, regression line, using cards sent to predict cards received. We know there was a correlation there. It wasn't significant, but there was a correlation, 0.8. And so in theory, by using cards sent, we could probably make a better prediction on cards received compared to either using the mean / if we say we're using the mean as a predictor, it's almost like saying we're not using a predictor at all. And so yeah, these will be the errors using this equation that we're going to go through. The least squares regression equation, where we are trying to minimize the error, minimize the total of all square prediction errors for y. If we have that -6, -2, the 2, and the 6, we're going to try to minimize those to make a better model, is essentially what we're trying to do. This is the least squares regression equation. So y equals b times x plus a. Y is going to represent our predicted value, how many cards we think that person will receive. This is what it'll look like when we're all said and done. So we'll be able to plug in an x variable, which would be cards sent, to predict cards received. So if we plug in 11 into this formula, we take it times 0.8, we add the 6.4, we get 15.2. And so what we're saying is, if that person sent 11 and we have to make a prediction using this least squared regressions, it's going to be a 15.2 roughly. So Y is our prediction. B and A, the B here and the A here, are both numbers that we get from the original correlational analysis, and we plug those numbers in. I'll show those to you. So B equals R, our Pearson's R, times the square root of the sum of squares Y divided by the sum of squares of X. So this is for B. We plug that in next to the X in the original equation. And then A is going to be the mean of Y minus B times our mean of X. I think it's 12 and 7. So we'll plug this B into the least squared regressions equation and the A in there too. And then that's where we get that this here. We'll eventually get to that 0.8 for the B, and we'll get to 6.4 for the A. And then, yeah, again, we can just plug numbers in to that equation, and we can get our predictions for each one. Here's another version of it. Sum of squares for X, sum of squares for Y. We would, again, have those from the correlational analysis. We have our R, so 0.8 times square root of 80 divided by 80 gives us also 0.8. Our mean for X was 7, mean for Y was 12, and we plug that into the formula. 12 minus that B that we just got, 0.8, times the mean of X, which was 7. We calculate that out, and we get 6.4, just like I was showing you. So the B is 0.8. Our X variable is our predictor that we're going to plug in, and then that plus 6.4 is the A. Here's just another version, if it helps you to see it a different way. So we have our R, sum of squares for X, sum of squares for Y, our mean of X and our mean of Y, and we just plug them in. So B, take that 0.8, square root of 80 divided by 80, 12 minus our 0.8 times the mean of X. And so if you need to, you can spend a little bit of time looking at this if you need some more time to make sure that it all makes sense. So we get this equation, and we want to compare it to a model with no predictors / the mean. And so we're going to see if our prediction is a better predictor. So we need our sum of squares for Y. We already have that. And then we're going to take each X variable and plug it into that equation. And then we're going to create a sum of squares based off of our prediction minus the actual value. And then we're going to compare that error to the error of using no predictor. I know it sounds like intense and a lot of things going on, but I think by the end of it, some of this will make sense. So again, here's our data set. Here are the errors just using the mean. Once we go through all this, these will be our errors using the equation. We have to get our sum of squares for Y. We would already have this in 80, but just as a refresher, it is, you take the mean, you take each one of our variables received, plug them in, take it minus that mean, and so we get a -2, a 0, 2, 6, -6. We already discussed this. You have to square each one because it equals 0. You square them, you sum them up. Our sum of squares using the mean or no predictor is an error, basically an error of 80. So now we will plug in each one of the X variables, our sent cards, into that equation that we got. So we're going to plug in the 5 for Andrea, the 7 for Mike, 13, the 9, and the 1 to get our predicted cards received for each person. And it's close. So like a 10.4 for Andrea, who had actually got 10. Mike was dead on, 12 and 12. Doris, it was a little bit off, 16.8 to 14, and so on and so forth. We're going to take these numbers now, our predictions, the 10.4, the 12, so on, and take those minus what actually happened to get our error. 10.4 minus 10, we get a 0.4, 12 minus 12, 16.8 minus 14, and we go all through those, just like all the other times. It would add up to 0. So we will square each one to get our sum of squares for our model. So the 0.16, the 7.84, we'd add all those up, and we get a 28.8, which essentially is telling us that the error in our prediction is about a 28.8. And if we compare that to an 80, that seems like we got quite a bit less error in our model compared to a model with no predictors. So it feels like we're doing good. 28.8 compared to 80, it does seem like that's a big difference to me. So we're comparing a model with no predictors, got that sum of squares of 80, versus our model using cards as a predictor, and we got the sum of squares of 28.8. Okay, that's kind of the background for it, and we'll go more into that, but I'm going to show you some stuff in SPSS real quick. We can run this. So we have our X and our Y, and these are the cards sent, cards received, just like they've always been. And the other analyses that we've done, we're going to click Analyze, Regression, Linear. We're going to move our X variable into the independent and the Y into the dependent, the cards received. We're saying that the cards received is dependent upon the cards sent. We just move those over, we click OK. We'll get some output. So we'll get a model summary, we'll get an ANOVA. We're not going to go into the coefficients today, but we will soon, sometime. So it's analyze, let me do it again for you. Analyze, regression, linear, and all we have to do is move over the X variable to the independent, which is this section here, and the Y into the dependent, and click OK. In that model summary, one of the numbers we're going to get is what's called R squared. And what R squared is doing, it is telling us how much of the variability in one variable can be explained by our predictor variable. So basically, like, how much of the variance are we going to soak up using our predictor variable instead of no variable at all? Basically, how much does our predictor account for in that variability? And so this is the R squared right here. There's two ways to get it when you just have the two variables. One, we have our R right here, which is our Pearson's R, which was 0.8. You can actually just take 0.8 times 0.8 to get, just like it sounds, R squared, which is a 0.64. What this 0.64 is telling us is that 64% of the variance in cards received can be explained by cards sent. That's pretty good. We got rid of like 64% of the error by using that sent as a predictor. Again, we could get that just by 0.8 times 0.8 to 0.64. But we can also see like the underlying mechanisms of how this works in the ANOVA table. We've not gone over ANOVAs yet, but we will go over them soon. This is kind of like a brief intro into what's going on in this table. If we look at the total sum of squares, 80. So that's how much error there was when we had no predictors or when we were using the mean as the predictor, if you recall, 80. Our model, the residual, what we got the error down to was 28.8. That's how much error was left after we used card sent as a predictor. If you take 80 minus 28.8, what you get for the regression line here is a 51.2, meaning that our model explained 51.2 basically of the error, which left us with 28.8. But our model, yes, it accounted for 51.2. So now think about it. If you were to look at this table, if we take 51.2 divided by 80, what would we get? 51.2 divided by 80 is going to give you 0.64. It's our R squared, which makes complete sense. It's like, that's how much we explained. We explained 51.2 of the error out of a total of 80. And if we just divide that out, we get the 0.64, meaning that 64% of the variance was explained by our predictor or our model, which is pretty good. So to sum up, cards sent is a better predictor than no predictor at all, at least like numerically. Is it significant? No. Unfortunately not. It is a 0.104. But again, this is going to be related to our sample size. If we had a bigger sample size, if we just double up the sample size to 10, we do get a significant finding. On the rest of this ANOVA table, we'll go through it here just to give you an idea of how this works. Our degrees of freedom we've talked about before. These are like how many of these numbers are free to vary given the mathematical restrictions, and that's one of the reasons, when everything's adding up to 0, it means one of those numbers is not free to vary. For an ANOVA, the regression model that we're going to look at, our total is going to be n minus 1. So if we have 5 pairs, 5 minus 1 to give us a 4. Our regression degrees of freedom is just how many predictors we had. And you can see it here. If you go down here to predictors, it gives us X. So we had 1 predictor. So our degrees of freedom for that will be 1. Predictors, there's the X. And then the residual is just going to be whatever's left over. So 4 minus 1. And so now we've divided those degrees of freedom out. We have 4, we have 3 left in the residual, and 1 for the regression. We are then going to take those sum of squares and divide it by our degrees of freedom, and it basically was like a mean sum of squares for our regression model, what was left. So 51.2 divided by 1 is going to give us a 51.2. On the residual, so we had 28.8 divided by 3 is going to give us a 9.6. So now we have the mean, sum of squares for the regression, for the residual. And then we'll talk more about this again when we actually do ANOVAs, the real ANOVAs. But we're basically like looking at the between group and within group variability. And what we do is we take that mean square for the regression divided by the residual, and it gives us 51.2 divided by 9.6 is 5.33, an F statistic. We've done Z and we've done T, and for this, for ANOVAs, we'll be doing the F statistic, and there is a table for that. I'll show it to you here in a second. So yeah, we get our, and we would have to meet some kind of a critical F value to say it's significant. So that critical F value for this, maybe 10 or 12, whatever it is. How we find out those, we go to that table, and we need our degrees of freedom. So when we write this up, we're going to write it up as F1, 3, and those are our degrees of freedom, 1 and 3. So we'd go to this table, we go to 1 on this top part, we'd go to 3 here, we scroll over 10.13. That's the critical F value that we needed to hit to get a significant finding. We didn't do it. We got a 5.33. If you look, again, if we just doubled up, if we had just 4 or 5 more participants somewhere in there, we come down here to like if we had 1 and 7, we just would have needed a 5.59 or 5.32. That being said, so that that value goes down the more participants you get, but also if we go back here and look at the math, some of these things would change. So like the 28.8, if we bumped it up to 7 or 8, that would now be divided by a 7 or 8, making this number smaller, making this number bigger. So again, one of the reasons that the sample size is going to matter is 1, the critical value that you need. You can see it goes down. We're 10.13, just added one more person, 7.71. So by adding more people, the critical value goes down. Additionally, it is going to change the mathematics inside this table. If we had, instead of 3 for the residual degrees of freedom, if we had a 6 or a 7, that 28.8 divided by 6 or 7 brings that down quite a bit, which brings the F up. But because our F is 5.33, it does not meet our critical value of 1013, so our model's not significant. And yes, I guess I already explained all this. How can we explain so much of the variance, 64%, and not be significant? It's just that we didn't have enough participants. And so yeah, that's how we'd write it up, P greater than 0.05. All right, let's see here. Maybe we can do it in our studio. You could open up a file with these, or these aren't too bad. We could just create this right here. So we put cent, the arrow, the line. We're going to put C in there, and then in parentheses we'll put a 5, 7, 13, 9, 1. Click enter. That created the variable cent. To create the variable received, same thing. Line the arrow, parentheses, 10, 12, 14, 18, and 6. Enter. I always mess it up somewhere. In this case, I did not put that C in front of it, which you need it to actually get it to create it. I always forget something. Enter. So now we've created sent and received. We're going to create a data frame to work with. I'm going to call it REGEX for regression example. So put the little line, or the arrow, the line, data frame. And then parentheses sent and received. Enter. If you just enter that data frame name in, it will give it to you. I do that to check and make sure that the data is actually there, and so we do see the sent and the received. Okay, so linear model, GAMES. This is doing a linear regression. LM equals LM sent this for, and then received. Basically, this is going to be predicting this variable, and then our data is going to be from REGEX, that data frame. Click enter. Looks like it worked. So what we'll do now is go summary, LMGAMES, and it should give us the results. Ta-da! And it did. So our R squared, 0.64, just like in SPSS. Our F statistic, 5.33. Our degrees of freedom, 1 and 3. And our p-value, just exactly the same numbers that we got from SPSS. I do have another example from the field textbook. he has, let's see what it looks like. These were album sales in thousands. So if you have 330, like that first one, it's 330,000. So it's sales, and then there were other variables to see if they predict the amount of sales. So we have adverts, airplay, and the image, how the band looks. The only one we're going to do today is adverts. We're going to do a simple linear regression, meaning that's just one variable predicting one other variable. Multiple regression, we would take adverts, airplay, and image to see if they predict sales. In any case, to predict sales from advertisements, we click Analyze, Linear, or Regression, Linear, reset it. So sales will be our dependent, and then we'll move adverts to this area here, the block 1 of 1. Just as an FYI, if we did want to do the multiple regression, we could just add those other variables in there. And we will do that at some point in the future. I don't want to overwhelm you, though, with this lecture. We get our results. So let's go back to the PowerPoint. So in this case, we get an R squared of 0.335, meaning that 34% of the amount of variance in albums sold can be explained by our predictor of advertising. So 34%. If you put your advertising budget at this much, you should get these many in sales. So it's a pretty nice way to predict that. 34% is pretty big. I don't think I mentioned, so there was, I think, 200 data points. You see how it just goes on and on. The idea of typing each one in those, you would probably want to have a file like this instead of trying to create a database, data frame in R. But also, think about the idea of doing this by hand. This isn't something you probably could have done by hand, 100 years ago. You could have, definitely you could have. But the amount of time it would have taken, it would have just been overwhelming. And so, I mean, look at these. The sum of squares is like 1.3 million error in that total. So it's like, it's too much. So one of the reasons that we can do all these, fancy statistical analyses is because of computers. And we probably wouldn't have done this kind of analysis. Most people wouldn't have, 100 years ago. In any case, our regression was explaining it looks like about 433,000 the error out of the total of that 1.3 million. And again, that would equal 34%. Our degrees of freedom in -1, how many predictors we have, whatever's left. We divide those mean squares out to get our F value of almost 100, which is huge. And SPSS does show it as P less than 0.001. But you know that, even at like 1 degrees of freedom, 1 over 20, I don't remember, the F was like 3 or something. So we have 100, which means it's huge. And this is how we would write that part up. A significant regression equation was found. F1, 198 are degrees of freedom. What the F statistic was, 99.59, and then our p-value, P less than 0.001, and also report the R squared of 0.34. We got that from that model summary, the 0.34, and we got everything else from the ANOVA table, the 1 and the 98, the 99, and the P less than 0.001. We could also do this one in R squared 2. I'm just going to pull up, again, instead of putting each one in, I would just copy this over. I would just, copy these over. This is going to give us a new data frame, REGEX, and we're just reading a CVS file. That's going to create that data frame. You can do this. So let's try REGEX. I'm curious. I think it's going to list everything. Yes. Well, not quite, but it listed quite a few of our variables there. You could just put head and then whatever you've called your database, REGEX2, and it'll just give you the first 5-6 lines. Okay, so LMGAMES equals LM sales predicted by adverts. Our data frame equals REGEX2. Hopefully it worked. Summary, LMGAMES. Ta-da. So if we go back to our PowerPoint, we can see the exact same numbers as in SPSS. Our F statistic here at the bottom, our R squared right above that, and our p-value. That does remind me, sometimes with RStudio, you're going to have to do you'll have to do something with the exponents in your head. And so if you see something with 2.2, but exponents 16 out, it's like it's really significant. It's a really small number. You see that there and a couple of other places. Or like here, so on adverts, the estimate these are the coefficients. We'll talk about those some days. It's a 9.6, but the exponent is -2, meaning that you would have to move that decimal place over mentally 2 places. So 90. So it would actually be 0.096 is what that is. One last thing to talk about, and we've already kind of gone through this. If you were given an ANOVA table like this with the sum of squares and you're told how many participants are in the study, you can figure out everything else. So for example, the total n, or degrees of freedom, will be n minus 1. So if we have 9, it's going to be an 8. Meaning, and then the regression, how many predictors do we have? There's just 1 cent. So we put a 1 there, meaning there's 7 there. Divide 102 by 1. Divide 57.6 by 7. Then divide 102 by 8 to get an F of 12.44. We go to our F table, and we go to 1 and 7. So 1, 7. To be significant, at the 0.05 level, you would need to hit a critical value of 5.59, or to get a significant P at 0.01, if we hit the critical value of 12.25, we'll do it. And again, we got a 12.44, so we just barely did it. So now we can put P less than 0.01. You might be like, who cares? But it is kind of neat. It's like if you have a P less than 0.05, we're like 95% sure, 1 out of 20 for the type 1 error, false positive. But if we get a P of less than 0.01, we're saying we're 99% sure. And so typically people will list whatever P value you hit on that critical value. So if you get a 0.01, that's more rare than a 0.05. 0.001 is more rare than a 0.05. Most people don't go out past 0.001. So usually it's just either 0.05, 0.01, or 0.001. Congrats on making it to the end. At some point, we'll come back in and we'll do multiple regression where we have multiple predictors, and we'll also look at the coefficients table. All right. Thank you very much for listening.